The most powerful medicine on this earth is the human spirit. Good evening and a very warm welcome to the series of international webinars organized by the Physics Department, RD National College, in association with Institute Innovation Council and internal IQAC cell. I'd like to congratulate Dr. Milind Kulkarni from the Physics Department, who has taken this initiative in organizing these webinars, which go right up till June 14th, mid-June. I'd like to welcome all the participants who have enrolled for this. A special thank you to the Physics Department, headed by Ms. Namrata Ajwani, Vice Principal and IQAC Convener, Professor Dinesh Himatsinghani. These webinars are happening under the aegis of the Placement and Internship Cell of RD National College. I wish them all the success, welcome everybody, and happy learning. I conclude with what the famous Olympic gold medalist said: dreams require effortless sleep, whereas aims require sleepless efforts. Thank you.
A very good afternoon to one and all. It's my utmost pleasure to extend a warm welcome to all the dignitaries, students, faculty members who are participants in today's webinar. On behalf of the Department of Physics, RD National College, under the aegis of IIC, Research Cell, DBT, IQAC, and a distinguished IC principal, Dr. Neha Jagtiani, I wholeheartedly welcome all of you to the third session of the International Webinar Series, which is on Real-Life Applications, Neural Networks, 3D Audio and AI by Mr. Nikhil Javeri, Research Engineer, University of Southern California, USA. Before we start the webinar, I'd like to introduce Mr. Nikhil Javeri, our keynote speaker. Mr. Javeri will be in Electronics and Telecommunications Engineering from Vidyalankar Institute of Technology, Mumbai, and MS in Electrical Engineering from University of Southern California, USA. His area of specialty is in machine learning and neural networks, psychoacoustics, and immersive audio digital image processing, speech recognition, digital signal processing, multimedia system design, random signal analysis, control systems, television and video engineering. He has vast research experience, many academic and co-curricular projects, professional certifications, publications and patents to his credit. On behalf of our inspiration and guide, the head of the Physics Department, Ms. Namrata Ajwani, I wholeheartedly welcome Mr. Nikhil Javeri for a wonderful session with us. Over to you, sir.
And television and video engineering. He has vast research experience, many academic and co-curricular projects, professional certifications, publications, and patents to his credit. On behalf of our inspiration and guide, HOD of Physics Department, Ms. Namrata Ajwani, I wholeheartedly welcome Mr. Nikhil Javeri for a wonderful session here. Over to you, Mr. Javeri.
Okay, thanks, Steffi ma'am. Thanks a lot. And I'll screen share my screen now, and I'll start with the presentation.
Yes.
Just give me
Sure.
one moment.
Thank you, Steffi madam.
Welcome, sir.
Okay, so can you see my screen now?
Yes.
It's visible.
Okay, perfect. So should I go ahead? Should I start?
Sure,
Yes.
sir, sure.
Yes.
Okay, perfect. So basically, my name is Nikhil. I'm a research engineer at Embody. I graduated from USC, the University of Southern California, with a master's in electrical engineering. So I basically deal with neural networks and 3D audio. So 3D audio is basically a space where you can hear sounds coming in from all the directions. So it's so basically what VR is to TV is what 3D audio is to audio. And that's something. So basically I'll be talking about how we apply neural networks in this domain, or the basics of neural networks and how we use neural networks to kind of create these amazing experiences which are applicable in real life. So I'll start with the presentation now. Okay, so basically a person who never made a mistake never tried anything new. It's a famous quote by Albert Einstein, who actually was, obviously, I mean, everybody knows Einstein. And why I wanted to put this out there was because I wanted you guys to kind of be open to new ideas, be open to new things, and never be afraid of making any mistakes, because that's the only way you will learn. So we'll start on this quote now. So basically what I want to do is I want to ask you guys a couple of questions to kind of gauge your understanding of how you guys or what you're aware of, and how you deal with mathematics and stuff like that, so I can pace myself accordingly. So here's just one of the questions. Given a sequence of number pairs, express y as a function of x, right? And here are your number pairs, and if any one of you can answer this in the next 30-40 seconds, then that would be nice. Just kind of guess and give me an answer. It's open to everyone.
Yes. Square minus 1.
Okay. So that's the correct one.
Y equal to square 1.
Now let's go to the next one. So if you're given a semantic sequence, what would be the results of these?
Nikhil sir, please unmute all. Then if possible.
Okay. Yeah.
Otherwise,
I have to.
Otherwise, participant can answer in the chat. They can use chat box.
Sure, they can use chat box as well. Will I have to unmute, or? Let me see.
Okay. Okay, Nikhil, no problem.
Okay. If yeah, so can you just hold on. Yeah. So if anyone has the answers, just let me know. If not, then I'll proceed ahead, and I can explain.
Nikhil, proceed.
Okay, so no problem. So basically, given these semantic sequences, right? King minus boy plus girl means queen, obviously. Whale minus human plus fin. So whale is actually a mammal, and humans are also mammals. So basically, we take the mammal aspect out and we add fins, so that leads to all fish that are not mammals. So basically, these sort of sequences are difficult for us humans to kind of wrap our head around, but these are actually easy for neural networks to understand, and that's where I'm going into. So neural networks are a space where basically you can actually encode any sort of a problem in an appropriate way and get a solution out of it. And it's very interesting. And what I'm going to do is I'm going to take you through how a neural network works, a very basic understanding of what neural networks are, and then kind of go over 3D audio aspects and how we apply neural networks to that front. What I want you guys to do is white minus red plus blue, right? I've not answered this question because I want you guys to think about it, and you can tell me at the end of the seminar. So with that, I will move ahead. So basically, what are neural networks? Neural networks are basically a child branch of economics and computer science. It's basically a nonlinear set of functions designed to model human perception. So basically, how humans perceive things, right? How our brains perceive things is what neural networks try to model. So it's very simple. Think of something like y, or the output, as a function of, or basically as a as a nested function, basically. So it can, like, think of it as f of g of h of I of x plus some constants. So if you can understand this terminology, right, you have almost understood neural networks. It's as simple as this. The next part of understanding neural networks just comes down to how you model these functions or how you choose these functions for the appropriate task. So basically what we do is neural networks has a mathematical aspect and a computer aspect or a computer science aspect. So in the mathematical aspect, what we do is we basically try to model these functions appropriately. And in the computer aspect, we then encode or implement these functions as computer algorithms to perform pattern recognition tasks. Neural networks are basically heavily reliant on linear algebra, probability theory, vector calculus, and statistics. So the very basic form of neural network is a perceptron. It's almost like an atom to an element. So neural networks are made up of multiple perceptrons. They are the basic building blocks of all neural networks. We can combine perceptrons in multiple ways, like how we combine atoms and molecules into substances. And then we can rearrange these perceptrons just like atoms, like a lattice structure, or it can be amorphous or even liquid, loosely bound. That just tells you how we can take perceptrons as individual elements of a neural network and then rearrange them to forms, to form structures that are tailor-made for specific applications. So this over here is basically a basic representation of a perceptron. What you have is a set of inputs, which is X. Then you have a set of weights, which is marked by W. And then what happens is you multiply individual inputs to individual weights. So X1 gets multiplied with W1, X2 gets multiplied with W2, and so on. And then these get summed to form your f of X, or basically a function. So basically you're approximating a function as a weighted set of inputs. So basically what I'm trying to say is, using these atoms, right, we can form different kinds of neural networks that are tailor-made to specific tasks. So a very basic kind of neural network is an artificial neural network, or an ANN, which is modeled as a set of perceptrons. And I'll talk more about artificial neural networks later. DNNs, or deep neural networks, usually have 3 or more layers, and they take in raw data directly. So basically, usually for neural networks, what happens is you have to pre-process or condition the data such that you extract good enough information out of it before feeding it into a neural network. That's something that's called as feature extraction or feature engineering, and we'll talk about that in a little while. Convolutional neural networks are usually for images, because images have an inherent structure, images or videos, where nearby pixels, right? You represent images in pixels. Nearby pixels are highly correlated to each other. Then there are recurrent neural networks, which are usually used for time series data like speech or text. And these are just some of the most common neural networks that are available. There are tons of neural networks out there with different kinds of structures and algorithms. And I've also mentioned a link where you can check these other neural networks. But what we'll do is we'll start with the very basic, which is a perceptron, and then kind of expand out into knowing how these perceptrons are applied to other sorts of neural networks. So broadly speaking, neural networks are used for 2 kinds of applications: classification and regression. Classification is basically the act of classifying a set of objects into classes. For example, given a picture of an animal, you can classify, a neural network can look at that picture and then classify it whether it belongs to a picture of a dog or a picture of a cat. And then these are similar samples of pictures of dogs, and these are similar samples of pictures of cats. And then the neural network will identify a boundary wherein if you show it a picture of a dog, it will actually label it as a dog. And if you show it a picture of a cat, it will actually label it as a cat. Or let's say if you want to gauge the housing prices, then that's sort of a regression problem. So basically, regression is an act of predicting values given a set of observations. So these red diamonds, right, are a set of observations. So if you consider these set of observations as the housing prices in, let's say, a neighborhood, right? And let's say let this be the square footage of the house in 1,000 square feet. So this is 1,000 square feet, this is 2,000, this is 3,000. And this is the price in tens of crores. So this is, let's say, 3.5 crores, this is 3 crores. So we have a couple of set of observations wherein you say, okay, roughly around 200 square feet is this much, 1,000 square feet is roughly like 2 crores, then 1,500 is roughly 3 crores, 2.5, 2,500 is roughly I mean, this guy got lucky, so he got it like at 2.5 crores. So if you think about that, and if I ask you in this given area, what would be the price of a house that is 1800 square feet? Then what we would do is we would fit a curve, which is also called as a regression, and then kind of project the value, or basically predict the value for 1800 square feet. So we'll drop a perpendicular to this guy and then say, okay, this is around 2.5 crores. So I mean, usually in real life, curves are not this simple. Like this is a very specific parabola that you see, and these are not very straightforward. So that's why you use neural networks to kind of model these high dimensional curves, which are, you know, of 100 or 200 polynomial degrees. So let's talk about basics of neural networks now. So basically, we know that neural networks is a complex set of nonlinear functions, which is used to map inputs to outputs. And neural networks basically learn through training. They're very empirical in their nature. So what that means is, given a set of observations, I can use those observations, input output pairs basically, and then map or find a function that relates the input and output pair. So if I have, let's say, if y is equal to f of x, right? But x, I don't have a continuous distribution of x. I have samples of x, where I have x1, x2, x3, x4, and so on. And I have y1, y2, y3, which correspond to those. So how can I get f given x1 and y1, x2, y2, or xi and yi, basically? Most often than not, neural networks need inputs that are curated or optimized for them to learn. So what does that mean? Basically, just in the case where you can't eat wheat in its raw form, it has to be milled in a flour. Neural network inputs also have to be conditioned, right? So basically what happens is you condition your inputs, or you extract features from your inputs such that learning becomes easier for neural networks. Or what I mean by that is, if x1 relates to y1, then what is going to happen is I'm going to transform x1 in some sort of z1, which is more closely related to y1. That's what it means. So basically, it's basically drawing information out of that x1 such that my learning becomes easier. The most common form of conditioning of data is called feature extraction or feature engineering. Now you might ask, what are features? So features are basically unique representations of an object. Take a few sports balls, for example. You have a cricket ball, you have a tennis ball, and you have a rugby ball. How can you differentiate between these three objects? You can say they're of different colors, they're of different shapes, they're of different materials, their weights are different, and so on. So basically, cricket balls are usually red or white. They have two parallel seams attached to it. Tennis balls are usually green, made out of hard rubber with only one seam attached. Rugby balls are oblong in shape. They're oval in shape, almost conical at their tips. So what we can do is, so basically what happens is, these features, right? We can take these features and kind of feed them to a neural network. So neural network, what it's going to do is it's going to look at these features and going to classify them into balls, into what object this is. So remember that neural networks are a set of functions, so they deal in numbers. So we can't just randomly throw features as, you know, strings at them, or, you know, features as, we can't say that, you know, okay, this is round. We have to represent that round as a number. So there can be multiple relevant features of these, and hence we use vectors to kind of represent this in a feature table. So if we fill in this feature table, right, what's going to happen is we are going to classify a cricket ball having a shape of round, color red or white, seems 2, and weights, it can have a weight between 155 to, let's see, 165 or something like that, grams. Tennis balls are also going to have a similar kind of statistics, where the shape is going to be round. The color is usually green. There is only one seam that runs around it, and the weight is going to be 55 to 60 grams. Rugby, on the other hand, has an oblong shape. The color doesn't matter in our case, and there are 4 seams to it, and the weight lies between 400. It's roughly like half a kilogram. So now what we need to do is, in order to tell your neural network how to interpret these features, we have to represent it in numbers. So what we do is we assign round as the number 1 and oblong as the number -1. We use the Vibgyor WK color scheme, basically, which is white and key or black, as, you know, an array of numbers ranging from -4 to 4. So basically, if we refill this table, it's going to be 1 for round, and -1 for oblong. Then you have the colors picked from these. Seams are anyways numbers, so you don't need to convert them into numbers. And weights are again numbers. Now the important point over here is that you also need to enumerate your outputs, which is basically your cricket ball, tennis ball, or a rugby ball. So you need to associate output labels or output numbers in our case, because neural networks deal in numbers, to these outputs as well. So we assign -1 to cricket, 0 to tennis, and 1 to rugby. So basically what we are doing now is we are vectorizing our features. So, and how does that help? It helps because now we can represent any ball as a set of features, right? So basically, let's say you have ball A, right, which is 1, -1, 2, 158.5, right? And the output label for that is -1. So if you get this set of observations, right, it's going to come to you like this. Then you have ball B, ball C, ball D, and you can have n number of balls. Now what we do is, for a neural network to look at this, hello? So for a neural network to look at this and then to predict this guy. So given n set of observations, we train a neural network to identify these relationships. So you have your input features, which is X, and then Y. So basically you have your X, Y pairs, and then you're going to find the underlying function, which will help you map X from X to Y. So basically, if you don't have your Y, then you can input your X and kind of predict your Y. And that is what neural networks will do. So let's say, for example, a real life application of this is, if you have a certain playing field which has all of these 3 balls, and there is only one staff to kind of collect all these balls and segregate it. So a machine is going to take the balls from this staff and it's going to segregate it accordingly, whether it be cricket, tennis, or rugby. So how can it do that? It's going to click a picture, weigh it, and stuff like that. So basically, after clicking a picture, it will understand that the shape is round. It will understand that the color is, let's say, green. It will understand that it has 2 seams. It will understand that it has a certain weight. And depending on this, it can say whether it's a cricket ball, tennis ball, or a rugby ball, and then it can basically sort things out. So that's basically an application of this towards automation, where you can use a neural network, train a neural network to kind of predict what ball it is, and then kind of sort it. So it'll reduce the load on the staff itself. The staff just has to give all the balls, collect all the balls from the playing field, give it to the machine, and the machine will sort it. So this is basically what machine learning is. It basically learned what features correspond to what ball, basically. So it found that input output relationship. Okay. Is everyone clear till now? Should I proceed? Or does anyone have any questions?
Yes, no problem.
Okay. So now what we'll do is we'll delve into the basics of a perceptron, the mathematical aspects of a perceptron. So as you see, you have your inputs over here, which exactly over here, as we have, let this be X1, let this be X2, X3, and X4. And we basically feed this into these weights, combine them, and then apply some sort of an activation function to get your output. So what is going to happen is, all of this, right, apart from the input, all of this is your f of x. But this f of x has to be learned. So what we are doing is we are modeling this f of x empirically. We are modeling it as a function of, we are assuming that it is a function of first multiplication, then addition, and then some sort of a nonlinear transform. So what we mean by this is, basically we'll take the inputs and then feed it, and thus it should spit out this output at the end. So that -1, +1, or 0, it should predict whether it is cricket, rugby, or tennis over here, given some sort of inputs over here. So how do we do this? So basically we have our inputs, right? We have x1 to x4, let's say x1 to xn in a very general case. And then what this is going to do is, this is, at this point, it is nothing but x1 w1 plus x2 w2 up to xn wn at this point. And then we're going to apply this nonlinear transform, which is psi, to this x1 w1 plus x2 w2. And if we treat these as vectors, then this will be x1 comma x2 comma x3 comma x4 blah 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 up to xn, and these will be w1 w3 w3 w4 up to wn. So basically multiplication and addition of these you can actually think of in terms of x into w transpose, right? So basically this can be, at this point the output can be modeled as psi of x into w transpose. So what happens? So our goal is basically, given a set of features, given a set of input features, is to predict whether the type of the ball is of cricket, tennis, or rugby. That's what the machine is going to do, right? It's going to sort those balls accordingly, but it needs those input features. So let's say you have all the equipment necessary to get those input features, which is weight, color, and the shape, right? So those input features will be fed over here. And now what you need to do is you need to train these weights, or basically you have to come up with a set of weights that generate an output where a cricket ball results into -1, where a tennis ball results into 0, and a rugby ball results into 1, right? So what we do for this is we start the training process by first gathering a set of training set, which is basically taking x number of or n number of different balls and then kind of getting their features and then assigning them and then kind of annotating them to be -1, 0, or 1, depending on whether they're a cricket ball, tennis ball, or rugby ball. So we basically show a computer that this is a cricket ball, these are its features. This is a tennis ball, these are its features. This is a rugby ball, and these are its features. But not all balls are made same, right? So because of which we have a statistic around every ball. So what happens is, cricket ball, it can be round, but it can vary in its weight, let's say. So over time, if you keep on playing with a cricket ball, it's going to get chaffed. Let's say a test cricket ball, right? Over a period of 2 days, over a period of an inning, it's going to get chaffed. So it's going to lose some of the weight. It's going to lose some of the shape. So it's going to lose some of the dimensions also. So what happens is, you can't exactly classify something into a very categorical class. You have to deal with statistics where you have a Gaussian distribution where, let's say, my weight can be 55 or 155 grams, or it can be 165 grams also. And let's say throughout the play of the cricket ball, it's going to reduce in weight from 165 to. So you have to account for all of these different weights. So what's going to happen is, in your training set, you're going to include all of these different balls with different features that all map to the cricket class. Same with tennis ball and same with rugby ball. So what happens is, we start with some random weights over here, and then we choose some nonlinear function, and then we kind of train this. So basically what training means is nudging these weights in a direction where after the training, these weights will be at an optimal position to say, given a set of input features, if I give it a set of random features that loosely relate to a cricket ball, it should output a -1, right? So for this activation function now, we're going to use a tanh function. And the reason why I'm using a tanh function is because at this point, right, so this activation function has to generate an output which is bound between -1, 0, and 1. So basically, whatever input goes into this activation function, it will basically get plotted on this x line, and then it will get projected out on the y-axis to kind of get your output. So basically, tan h has a special characteristic where its range is from -1 to 1, right? So it becomes ideal for us to kind of have these three classes. So basically, if you want to predict -1, that means at this point, my input has to land somewhere over here. So basically, my weights have to be tweaked in such a way that if I see that specific input, my weights land my point over here, so that when it gets projected onto the curve, I get an output of -1. Similar for a tennis ball, my output at this point has to land somewhere over here, so that when it gets projected on my curve, it lands near a 0. And for a rugby ball, somewhere over here where it lands near to 1. So basically, what we do is we pass these observations that we have through the neural network with randomized weights. So what we do is we take these weights and we initialize This is the training procedure basically. We take these weights and we assign random values to them. So these are all scalars now. So let's say you have -1 and this got randomized, this got initialized with, let's say, 0.85. This got initialized to like plus 0.7. This got initialized to -0.1 and stuff like that. So it's just random. So what's going to happen is after feeding in this multiplication, basically, this vector multiplication is going to yield into some random value over here. But we know what the output value should stand for in this training procedure, because we know in this training procedure we have an input and its corresponding output, and we're training the function to find this function in between, training the neural network to find a function in between. So what we do is we have our output and we have our predicted output, and the predicted output is after we pass the input features through these random weights. So what happens now is we need to nudge our weights in such a direction that the perceptron generates a valid output. And how do we do that? We know how much it is off from the actual output that we're trying to reach, right? So basically, let's say if you're training for a cricket ball, right? If the training example that you're showing the neural network is that of a cricket ball, then what is going to happen is you know that the output label should be -1, but it generates something like a 0.2, right? So now what is going to happen is this is going to be -1, this is going to be 0.2. So you know that your error is going to be -1 minus 0.2, which is -1.2 squared, right? But how do we actually use this error to nudge the weights in a direction which is going to help us train, or which is going to nudge these weights in a direction where it will generate a valid output? So basically what happens is if you see this function, right, it is nothing but the MSE function is nothing but a parabola. It is a squared function. So basically y is equal to x square. So this function is going to have a minima, and that is exactly what we're trying to achieve. We're trying to minimize the error such that a set of inputs get mapped exactly to a set of outputs, right? So what we do is, in order to find minimas, analytically what we do is we use gradients, right? We use the single derivative, and then we find the zeros, and then at those zeros we use the double derivative to check the slope. And depending on whether the slope of the double slope of that point is increasing or decreasing, we mark it as a minima or a maxima. So similarly, what we do is we use gradients to train neural networks as well, to kind of get an idea of how to nudge those weights in order to get the right output. But because we have so many observations, because the hyperplane that we're going to train on is going to be so huge because of those number of observations, that it becomes difficult to compute gradients analytically. So what we do is we use numerical methods to approximate these solutions. So for our loss function, right, it's shaped as a parabola, right? So what's going to happen is, let's say tan h of x into w transpose, which is our output, which is our y hat, lands somewhere over here, or let's say somewhere over here. The gradient of the loss function at that point is going to give you the direction towards the minima, right? This is called as gradient descent. So basically the negative gradient is going to give you an exact direction of where you should head. So using the negative gradient of the loss function, we are going to update our weights such that in the next iteration it is going to be a little closer to the minima. So if you look at this point, then the gradient at this point is pointing downwards. So basically the gradient at this point is negative for b. So what happens is, if you take the negative of b, then it's going to tell you to move in the positive direction of x, which is in this direction. Versus at this point, the gradient over here is the negative gradient over here is going to tell you to move in this direction. So what happens is, gradient by gradient, example by example, you start nudging this point to the optima, and you stop when you hit the optima. So let's get into a little bit of math. So for our output, y hat is nothing but tan h of x into w transpose, right? But what we need to do is we need to optimize the weight such that for all inputs in a training set, we minimize the loss function, right? Thus, in order to see the direction in which we have to nudge the weights, we need to take partial derivatives of the loss function itself with respect to individual weights. That's how we'll come to know for individual weights, how should we change them. So our loss function is nothing but yi minus yi hat squared, and yi is the actual output, yi hat is the predicted output for that specific example. So dou L by dou Wi by chain rule is going to be dou L by dou y hat times dou y hat by dou z times dou z by dou Wi. So basically dou L is a function of yi hat, right? So what we're going to do is dou L by dou y hat, and then dou y hat, because y hat is itself a function of z, which is nothing but this guy, x into w transpose, which is psi of z, times dou z by dou w, and then z is x into w transpose. So basically z is a function of w as well. So for these partial derivatives, it will become dou L by dou y hat will become 2 times y hat minus y. Dou y hat by z, which is nothing but dou tan h of z by dou z, which is nothing but 1 minus tan h square of z. And then dou z by dou wi, which is nothing but dou of summation wi xi, right? That's the input that we fed after multiplying with the weights. That by dou wi. You can pull the summation sign out, and because it's just dou wi, all the other terms, which is, let's say if this is w2, then this is going to be dou w1 x1 plus dou w2 x2. But w1 x1 is going to be a constant for something that is, partially derivated with respect to w2. So the only thing that remains is xi in this case. So in case of w2, it will be x2. So what you can do is, for that specific example, right, when you are coding it, what happens is, in terms of programmatically, you compute all these values. You already have x1, which is your input feature. You have already computed z as a middle step where you are feeding it into the tan h function, and you have y and y hat as well. So y hat is the predicted output and y is the actual output. So combining all of these, you come up with dou L by dou wi. So how do you use this? So basically, what we do is we update the weight. So in the next iteration, we're going to change the same weight wi as the previous weight minus some constant alpha times the gradient of the loss function with respect to the weight. Why am I using minus over here? That's because of the negative gradient. So when we said negative gradient is going to point us to the minima, and we want to minimize our loss function, that's what the loss function stands for. This is what we're going to do. So basically, and what is the significance of this alpha term over here? So this alpha term is actually called as a step size, right? Or a learning rate. It depends on, it can be interchanged, so it doesn't matter. But what is this alpha term going to do is, let's say if I choose some value of alpha, or let's say if I choose alpha as 0.1, then I have some direction which is given by my gradient, and then I have some magnitude given by my alpha. So this direction times the magnitude is going to nudge this weight to here, then here, then here, then here. If I have a very big alpha, it can jump directly over here. If I have a very small alpha, it will take smaller steps, thus a longer training time. So basically, it is very important to get the right judgment of alpha. And in neural network training, what we usually do is as time progresses, we decrease the value of alpha over time. So what happens is we started with a very large gradient to kind of get it very close to this point, and then we decrease the value of alpha to kind of slow it down till it reaches the end, till it reaches the minima. So going over the basics of the neural networks again, you have input output pairs, and you have n such observations in your database where you have your input output pairs for different kinds of balls. Let's say for cricket balls, you have 10 different kinds of balls in different states, and you want to capture those examples, all of those examples. So you include all of those. So what happens is, let's say you have n number of examples. Once you show the computer, once you show this algorithm all these n examples, it's called as one epoch. Neural networks are basically trained for multiple epochs until they achieve certain convergence metric. So usually a good convergence criteria allows for a training validation set error to be, let's say, 5% or lower. And what does that mean? when you have these n number of observations, right, you don't use all these n number of observations for training. What you need to do is you need to split your training set, your set of observations into a training, validation, and a test set, such that you can use a validation set to make improvements on your neural network. So you show the neural network only n number of samples, or only, let's say, n1 number of samples, and then you test it on the other remaining n minus n1 number of samples to kind of figure out how you can improve the neural network. And that's where this validation set error comes in from. There can be multiple convergence criteria depending on the application. So every application is different, and you can tailor your convergence criteria according to that. So basically, the main stages of a neural network can be portrayed as gathering the data. You have to collect all your observations and kind of, have these relationships already associated with it. Then you perform some feature engineering to kind of extract semantic information. So given a cricket ball, right, the features that we extracted were shape, weight, the color. Then you design a neural network which takes in these features. So basically, you extracted semantic information from an object or from your observations. You fed this information to the neural network to kind of train it, to map it to a certain class. Then you train it. Then you test your neural network, and then you improve your neural network, whether you want to make some tweaks. So mind you that what we saw right now was only a perceptron. It was literally an atom inside the neural network. And like that, there are multiple atoms inside the neural network. So that's what we're going to do next. So when we speak about perceptrons, right, these are just atoms. These are just nodes. So one perceptron is going to be one node in an actual neural network. That's what a neural network is. So you can see how complex it can become. So imagine this being one layer and hundreds of these, and each of these nodes as one perceptron. So this first perceptron is taking the first three inputs. You can tailor the inputs as well. This perceptron is taking the first three inputs. This perceptron is taking some next n inputs, or depending on. So you can tailor these neural networks to kind of or arrange and shape these neural networks in any way you want to kind of generate the output. So let's say you have three outputs over here. They wanted to get some more information, whether whether it was a cricket ball, whether it was in a good shape, whether it can be used again, stuff like that. So all of these things can be learned by a neural network at the same time. So neural networks are nothing but multi-layered perceptrons. So with that concept in mind, we'll move ahead. Just give me 1 minute. So what I showed previously was an artificial neural network. Similarly, you have convolutional neural networks that operate on images, as I said previously. So what happens is image patches, right, are highly correlated. So if you look at the center pixel has a very high correlation to the pixels that are next to it. And then they are basically quasi-static in terms of how they're spread out. They're very low frequency in nature and very quasi-static. That means they don't abruptly change. So this white patch, right, there is a huge white patch over here. Or if you talk about this gray patch, right, then there's a huge gray patch over here. So basically, even in real life, right, if you look at my photo, right, or my screen, or my video feed, on my face, basically you have a large area of the same color. So basically, there are not a lot of variations. They're very slow moving, very low frequency objects, these images. So what that means is we have to come up with a new strategy to kind of learn or extract features from them. And that's where convolutional neural networks come in, where they extract local features from a window and then kind of make sense out of those local patches until they reach a final solution. And these are nothing but your layers of the neural network that kind of train these weights. So the weights over here are also windows, which kind of determine, they kind of scan through, like literally scanning through an image and kind of recognizing, okay, what object is where. That's what these weights get trained for. Then you have recurrent neural networks, where if you have a time series data where the history matters a lot, you have your output as a function of input and an intermediate output that was generated by the previous time sample. So here you're generating an intermediate output, but what you're doing is, for the current output, I'm using my input as well as the previous history or my t minus 1 sample intermediate output. So that was the introduction to neural networks. I probably might have gone a little fast. So if I'll stop over here, and if anyone has any questions, I can answer them right now. We'll take a 1 minute break also before we get into 3D audio.
Nikhil, we will take after completion of this.
Okay, no problem.
Okay.
No problem.
We will complete all session, and then we'll take questions from our parties.
Okay, no problem.
Okay.
Okay, so I feel that neural networks is just one aspect. I don't know if you found it interesting or boring, or how much I made it boring. But we'll move on to 3D audio, which is I think a more interesting approach because you all are physics students. I think you will appreciate this more. So what does 3D audio mean, or what is audio in general? So we'll start with sound. So sound is basically an energy-based event in space and time whose energy flows to a listener, right? It needs a medium and the energy flows to a listener, and that listener interprets that energy as sound. Audio, on the other hand, is an electrical representation of sound. Audio and sound are not the same. What you hear is sound. What is represented on your in your computer as wave files, as MP3 files, is audio. So as with any event in our universe, the origination of sound is tied with 4 dimensions, space-time, which is X, Y, Z, and T, which is the 3 axes that we have, and time. These coordinates are usually expressed relative to the listener. So how do we consume sound? In order to consume sound, or in order to consume audio, you have to capture it in order to electrically represent it. So we have to use a transducer of some sort to kind of capture it. And the best kind of capturing device for sound is a microphone, which converts sound energy into electrical energy. So what happens is, if you look at this part, right, if you're using a microphone, what is going to happen is sound waves are going to hit on a diaphragm that is positioned inside the microphone, which is going to then move this magnet that is there. And this moving magnet is going to, by Gauss's law, this moving magnet is going to cause electric currents in this coil. So basically, you have an electromagnet that is proportionally driven with respect to the sound that is incoming. That's how you represent the sound waves, the sound waves. So, but so if you record someone with a microphone, let's say some person is singing, or Arijit Singh or someone is singing, and you record them with a microphone, and then if you listen to it, will you get the same kind of perception as if you were there listening to him live in a concert? I don't think so. That's because the microphone bit inside our ears is only the eardrum. It is only the eardrum. There are multiple things that happen to, I think there is some echo that is happening. Can people mute? Okay. I feel there is still some echo that is happening. I believe. Okay. Yeah. So basically what happens is, when you're listening to a concert, right, sound arrives at your ear, but then it actually reflects refracts off of the cavities of your ear, the outer ear, which is called as the pinna, then goes inside your ear canal, and then hits the eardrum, which is modeled as this microphone. So basically, if you listen to only a recording of the microphone, it is not going to sound as if it is spatialized, or it is 3D in nature, as if the sound source is actually outside your head. Most of the times when you hear some sound on a set of headphones, what's going to happen is you're going to feel as if the sound is internalized in your head, and you won't be able to accurately place the sound in a particular direction. You can't say whether the sound is in front of you, or 30 degrees to the right, 30 degrees to the left, or stuff like that. So we as humans, what happens is, when a sound originates, let's say for this specific user from a top view model, it originates over here and it reaches both your ears, right? But before reaching your ears, what happens is it's going to face some occlusion, it is going to arrive at one of the ears earlier than the other ear, because of which we as humans are able to tell where sound is coming from. If you see, or if basically if a plane is flying over you, you immediately look up because you know that the sound is coming from up. Or if someone behind you calls you, right, then you immediately turn behind because you know that that sound is coming from behind. That same perception you cannot get if you're wearing just a piece of headphone, just a pair of headphones, and that sound that you're listening to is recorded via only a microphone. So there are four fundamental things that happen when a human listens to the sound, as opposed to if that same sound source is captured by a microphone. The sound reaches one of the ears earlier than the other ear. There is an exception where the sound is bang in front of you and it reaches both the ears simultaneously, but I'll get to that later. B, the sound reaching to the closer ear is also slightly louder perceptually. So if it is a little off, right, if it is little to the right, then it has to travel a lesser distance to the right ear than to the left ear, because of which it is slightly louder, let's say like 0.5 or 1 dB louder. Head and body occlude the sound, because of which certain refractions happen. So basically, if the sound source is slightly to the right, what is going to happen is, for my right ear, it is going to take a direct path, direct line of sight. But for my left ear, it is going to get blocked by my head. Some part is going to go straight through my head, some part is going to get refracted. And the shape of the ear, basically, the shape of your pinna, which is unique to every person, helps in major reflections and refractions, giving a unique signature to the sound entering the ear canal. And we as humans, we grow up with acknowledging these differences that you get throughout your growing up process. So it's basically some sort of a reinforcement learning where you see and you hear and you interpret it. So basically, if someone calls you from, let's say, 30 degrees to your right, starting from 0 being the center, then you immediately look at that, you confirm that the sound was coming from that position, and you tell your brain to wire itself. This is all subconscious. This does not happen consciously. You don't literally tell your brain, but it all happens subconsciously, where you feel, where you see, and your brain automatically recognizes that, okay, this sort of a signature to my sound, because it's going through all of these different processes, is mapped to this point. This point is mapped to some other signature. The good part is that all of these signatures are external, which is with which we can actually measure these and kind of model these. So we'll look at these four fundamental cues individually now. So first is interaural time difference. This happens where you have a sound source that reaches both the ears, but one of the ear it reaches earlier because it has to travel a lesser distance. So basically, the sound source over here, let's say this is 30 degrees to my right, it reaches the right ear before my left ear. So if you drop a perpendicular over here, then DL will be equal to DR till this point. So D diff is this guy, where DL has to travel an extra distance. So basically, your ITD is the time taken, or the difference between the time taken for sound to travel to DL versus to DR, right? So how much is the ITD? Now ITD will be the time taken for sound to travel this much distance, because till this distance, both the paths are equivalent. So basically, that's D diff by V sound, or DR minus DL by V sound. It's usually in a few milliseconds for humans. Interaural level difference. Similarly, what happens is, because the sound had to travel a lesser distance in DR, it is going to be slightly louder. If you talk about intensities, right, then you have your wave fronts, which are going to hit over here, and the area, or basically the pressure divided by 4 pi r square, because dr is lesser than dl, the energy is going to be more concentrated per unit wavefront, as opposed to DL, where it is going to be more spread out, because of which the energy that you will receive when you multiply with the cross-sectional area of the ear is going to be lesser. And that difference of levels is called as ILD, or interaural level difference. ILD is usually in a few dBs for humans. Then you have body occlusion. So what happens is, DR, right, it goes straight through line of sight and reaches your right ear. But DL, right, it is going to occlude. So if some sound is coming from this direction, it is going to hit my nose. For lower frequencies, because their wavelengths are so big, they'll just pass through. pass through my skull, pass through my brain, everything, and hit the ear canal directly and kind of vibrate it. But for smaller frequencies, what happens is as you go higher in the frequency range, they start interacting with your skin. So around 1 kilohertz, right? That is where you have like I think, or 10 kilohertz. That is where you have like the 3 centimeter wavelengths. These wavelengths start creeping up the skin. So basically, they take different paths. So they hit the nose, they go like this. If a sound is coming from here, they go like this. So they take different paths, and that obstruction is known as occlusion. So basically, you have your low frequencies that pass directly through the skull, which is the green line. You have your mids and high frequencies, which bend about the head to reach the ear, and extremely high frequencies, which are so small, like let's say 15 or 16 kilohertz, they never reach because they have to travel extraordinary amount of length to kind of reach the ear canal. So what is happening? The same sound having the same frequency signature, those high frequencies are reaching here, but they're not reaching over here because they die down while reaching over here. So that's what body occlusion brings. And then you have your pinna effect, where basically sounds, basically the wavefront hitting your pinna is going to get reflected and refracted from the different folds and cavities in your ear. And believe me, all humans have a different ear shape. It's almost as unique as fingerprints. So if you look at someone else's ear and your own ear, you can take a picture and kind of compare. You will see tons of differences, tons of size and shapes and whatnot. This is a 3D structure where you form resonant cavities, Helmholtz resonators. Actually, it's a very complex Helmholtz resonator, so you can't model it that way, but you can still think of it that way. These nooks and crannies basically cause reflections and refractions of a very unique kind, because these refractions and refractions are dependent on the shape of your ear, right? And because it's unique to every person, the kind of reflection and refraction that's going to happen is going to be unique to every person. So this filtering is directly related to the shape of the ear. If you combine all of these four fundamental differences or fundamentals of sound that we spoke about, if you combine all of them together, then you get something called as the head related transfer function, or HRTFs. And those of you who might be playing games, right, let's say CSGO or PUBG or whatnot, you have the inbuilt HRTF function available over there, but they actually model it from a very generic perspective, which does not work for most of the human beings. So how do you define HRTFs? So HRTFs basically are described as a ratio of sound intensities between the presence and absence of head and ears. So all of these four things that we spoke about, right, they were in the presence of the head, right? So in the absence of the head, if you place a microphone over here and gauge the sound intensity, you get some intensity. Then place a head, and what you do is you place mics inside the ear canal. So you literally have a block meter measurement technique where you stick a microphone inside the ear canal, and I'll show you an image after this. And then what you do is, for different angles, you shoot sounds or you shoot white noise pulses, and then you record it at that point. So these white noise pulses for different directions are going to go through different paths for that specific subject, and then they're going to get captured. So you get two sets of HRTFs. One is for the left ear and one is for the right ear. So left ear is obviously described as IL by IO, which is IL is the intensity of the sound at the entrance of the ear canal, and IO is the intensity of the sound at the head center when the head and the ears are not present. Similarly for the right one. So basically, HRTF was coined by Blauert in the 70s, and MIT Media Labs after that started performing measurements with a dummy head, which is shown over here. This is called as a Hatch dummy head and torso system. And what they do is, this is a removable ear. It's an ear mold that you get multiple types of these ear molds of different shapes and sizes, and then you can place sources like these, and you can along an arc and shoot white noise pulses to measure basically from what direction how it's going to look like. And this is a block meters measurement where you have the microphone inside the ear. And trust me, this is a very tedious process to go through. So what happened? This is a turntable. So basically, you map all the different angles going from plus 90 degrees, which is above your head in a spherical coordinate system, all the way down to, let's say, negative 60 or something. and then you move around by 5 degrees and all of these happen again. Then you move again by 5 degrees and all of these happen again. So measurement itself, so measurement of an HRTF takes about, I would say, like 4 hours for a very coarse measurement, and up to like 12 hours for a very fine measurement as well. So it is very exhaustive. The subject has to sit very still. If they move even a little bit during the measurement, then you have to do the measurement all over again. And because every individual person has a very unique ear shape, it becomes very difficult for every individual person to kind of get their own HRTF, because you literally have to go into a lab and kind of get yourself measured. So now what we'll do is we'll talk about one of the databases that have captured these HRTFs for different subjects, and we'll talk about the characteristics of what we see. So there is a database called CIPIC, which was developed by UC Davis, which is University of California in Davis, which is about a 2 hours drive from Silicon Valley, where I live. And what they found was, for let's pick up one subject, which is subject 3. For 0, 0, which is right in front of you, so that's azimuth and elevation. So basically, azimuth goes horizontally and elevation goes vertically. So for 0, 0, which is bang in front of you, the blue curve represents the left ear measurement. The red curve represents the right ear measurement. So if there were no ears, then you would see a flat line on this frequency graph. And this is a semi-log graph. Basically, you have the dB scale, and you have the frequencies over here, which go from 100 to 22 kilohertz. So you see these different frequency variations, right? This is very characteristic to the pinna of that particular subject. So that particular subject's pinna was causing some notches. These low regions, or these valleys, are called notches in the HRTF domain. They are causing notches, which are caused by refractions. Basically, there is a dip in the sound for those particular frequency regions because the ear is refracting or reflecting it in such a way that that part of that specific frequency region doesn't enter the ear. And then there are resonances over here and here, wherein basically you have crest on crest or trough on trough after reflection and refraction, which is also specific to that shape, because only that specific shape can cause this, which is basically doubling or resonance of sound, which is amplification of sound. So you have notches and resonances, which uniquely define an HRTF, and that is very much uniquely tied to the shape of the ear. If you move the sound source to 30,0, which means 30 to the left, then you have the sound at the left ear being louder than the right ear, which is obvious, because if you move the sound source to the left, 30 degrees to the left, it is going to hit the left ear first. It's going to hit the left ear later. The right ear later. It is also going to have a larger amplitude at the left ear than the right ear, which is what you can see over here. And it has a different characteristic as compared to this. If you see the predominant notch, right, the minus 20 dB one over here is occurring roughly at 7 dB. Whereas over here, the dominant notch is occurring at, 7,000 kilohertz or 7,000 hertz. And the notch is occurring at 10,000 hertz. If you move it in the other direction, then it's closer to the right ear. So you get red being the right ear is at a higher amplitude than the left ear. And the signature of the HRTF also changes. You don't get the same, you don't get the same kind of, replication. So that just tells you that, the right and the left ears themselves are different with respect to each other as well. They have a high degree of correlation, but they are a little different when compared to each other. Go to the next one, where you now go into elevation. So if you go upright, then what is going to happen is you see this dominant notch moving away. So if you see this notch, it is at 9 kilohertz. If you move 30 degrees up, 30 degrees in elevation, you see it at 11 kilohertz almost. Then if you move it more up, then it's going to go at 12 kilohertz, and there's going to be another notch, which is basically this notch that moved ahead, which is going to be at, I think this will be like 15 kilohertz or something. So as you move up, your notches start moving ahead as well. And you start losing some characteristics in the lower frequency regions as well. If you go behind, which is 150 degrees or 180 degrees, like if you take this elevation and go all the way behind your head, then you start seeing these low frequency effects and very weird behavior because of your ear flare. So what happens is your ear flare, because your ear crops out of your head, sounds coming from the behind are naturally attenuated when they hit the ear flare, because of which you're going to get this phasing and some low frequency audition where you have this high low frequency bands as compared to this guy, where you have where you can see that this curve and this curve are not the same, where it kind of elevates in the low frequency regions, and you have very obscure, very sharp notches that are characteristic to the regions behind you. So 0,150 is right behind you, center and right behind you, but just a little elevated, and 30,180 is bang behind you, but a little to the left in the azimuth. So that's why you see that the left ear has a larger energy than the right ear. And these, and now you might be now you might ask how much different could different subjects be. So if you compare subject 3 to subject 9, which are two subjects in the database, for the same angle, they have vastly different HRTFs or vastly different frequency signatures because of the vastly different ear shapes. And if you look at all the subjects, right, there are about 45 subjects in that database, because it's a very tedious process to measure. That's why only 45. You will see that all of these 45 have vastly different frequency patterns, vastly different unique signatures, because of which, if you, okay, I'll kind of get to that. So if you see over here, this guy has a notch at around 7 kilohertz, and then a sharper notch at around 9-10 kilohertz. Whereas this guy, he has a notch at around 6 kilohertz or something, and then another sharp notch at 7 kilohertz, a resonance at, let's say, 12. This guy has a resonance at 12 as well, but not with a similar Q factor. So there are a lot of differences that make HRTFs individualized. So this is just the analysis aspect. So if you want to create a 3D experience, what you do is you take these HRTFs and you embed them into your earphone. And once you embed them in your earphone, right, sounds coming or a microphone recording basically gets convolved or gets multiplied with these frequency patterns and then get fed into the earphone, because of which you get a feeling of spatialization, or you got a feeling of having 3D audio or sound positions actually being localized around you with great amount of accuracy. That is only when you use your own personalized HRTF. If you use a very generic HRTF as the one that's given in CSGO or PUBG, some people whose ear shapes align with that specific HRTF will get an accurate image. Or the vast majority whose don't align will not get a good representation. The applications to 3D audio are endless. You can imagine having a home theater on a pair of headphones. Let's say you have a pair of 500 rupee headphones, but you still want to feel as if you're going to a Dolby Atmos theater. You can get your own personalized HRTF and listen to a movie using your headphones, and it'll actually sound like that. Or hearing aids, for that fact, where people with hearing aids actually have a lot of problem telling directions. So you can actually capture their HRTFs and embed them in the hearing aid, which will give them a sense of direction. It'll make their lives better. And the applications are actually numerous for gaming, for entertainment, for healthcare, and for defense as well. Like, there are numerous applications that you can, use HRTFs in. So what we do as a company, I work at Embody, and Embody is a company that creates personalized HRTFs. So as I told you, the measurement technique for HRTFs, right, they take about 12 hours to get a good enough HRTF. What we do, but we know for a fact that HRTFs are a function of the human ear and head. So heads actually don't matter that much. They do matter, but don't matter that much. The ears are the main reason why, or the pinnas are the main reasons why we have such drastic frequency signatures. What we do at Embody is we take a picture of your ear and we use a lot of neural networks to predict your HRTF in a matter of 30 seconds. So we go straight from about 12 hours and do the same exact process in 30 seconds, you just have to submit a picture of your ear. What we do is we use neural networks to kind of extract where the ear is, what kind of features uh, the ear the ear encodes. So basically, if you see, right, for these guys, there are some representations of how sounds of different intensities and different from different source positions hit the ear and excite different parts of the ear. So we use neural networks to kind of predict these parts. These are also known as Shaw modes, where you have different resonant cavities of your ear, and which are very specific to individual ears. And we use neural networks to kind of analyze your ear shape and kind of predict at what frequency what region will resonate, what region will kind of reflect sounds out. So at Embody, what we do is we use machine learning for multiple and kind of chain machine learning into a pipeline to form this neural network, to form this HRTF predictor. So the first task in that is basically to isolate where the ear is from that image. So for that, we use machine learning methods such as a regional neural network or a segmentation network or YOLO neural network, which basically isolates exactly where the ear is. Then we use some sort of a feature extractor neural network, which is basically some regression models, some autoencoders to kind of isolate the unique properties or the unique features, just like how for that ball we had the shape, the size. The shape and the size of the human ear is actually very important because that's what directly translates to how you're going to hear sound in 3D space. So we use a neural network to basically calculate those features as well for us. And then we use some sort of an HRTF prediction algorithm to map those features to an HRTF. So basically we use these features and we can fairly accurately say that if this width is roughly around 3 centimeters, so 3 centimeters is roughly going to interact with what, 10 kilohertz? That is what it is, right? So 343 divided by 10,000 hertz is going to be roughly 3.4 centimeters. A usual human ear is about 6 to 7 centimeters by 4 to 5 centimeters, and then the flare angle and everything matters. So yeah, so starting from, let's say, 6 centimeters onwards, which is about 5 kilohertz or something onwards, which is about somewhere over here, all of this information is all dependent on the pinna. Everything else is the head, which is roughly similar for people. It can vary depending on, if it's extremely small, if the head is extremely small or extremely big. But after that, after 4 to 4.5 kilohertz, everything is dependent on the pinna. So basically using just a picture of your ear, we can extract all of this information. So we use different machine learning tasks or machine learning algorithms and train them because we have this set of the ear and its corresponding HRTF. We go from that image to this HRTF in under 30 seconds by using this machine learning. So this neural network actually, or these sets of neural networks help us to solve a real life problem, which actually takes you about 12 hours and kind of compress it into a matter of seconds, such that, any random person can, get an experience that is immersive and can be mind blown by, the power of technology and the power of neural networks. It's pretty impressive. So that was it. That was my presentation, and we can now head over to questions. I'll stop my screen sharing over here and I'll give the handle back to Milind sir and Steffi ma'am.
Yes, thank you, Nikhil. Very informative, Nikhil. Yes, now question answer session is open for all. If you have any question, you can ask. Nikhil, unmute all. Otherwise, you can write question in chat box.
Okay. So I think Chandrajit is asking,
Yes.
What are the disadvantages of artificial neural networks? So disadvantages as such, there are multiple. I mean, as with any technology, it's basically how you use them in terms of is what is going to cause those disadvantages. In terms of technological perspective, you can say that they oversimplify some tasks which should not be. They do miss out on details if you don't train them properly. Then there are moral disadvantages as well, where Xsense is a company from China actually that does facial recognition, like we've heard, and kind of rates humans. So that from a moral standpoint, it is very disadvantageous as well. So yeah, that's that. Next, I have Mujahid Hussain. It is said that coupling between neuron is related to memory. Coupling between neuron is related to, so basically if you're drawing parallels to the human brain, right, not all neural networks are kind of formed based on that front. There are different types of neural networks. Mostly, so basically all these neural networks, right, all the neural networks in the world, if you combine them together, will form your brain. So you have bits and pieces that form different kinds of neural networks. So you say coupling between neuron is related to memory. If you can elaborate more, I can talk more about that. I'm not exactly understanding what your question is. In the meanwhile, I'll move to Jessica's question. So she's saying, by your explanation, I realized that ear pinna is very important for hearing, whereas biology says that ear pinna is vestigial. So is it possible to create an HRTF for a person who has lost his or her ear pinna due to an accident? Yes, it is. It is very much possible. So what we need to see, I mean, there are some downsides to it. If we have a picture of them with their ear before they lost their pinna, with our technology you can. Otherwise, you will need the physical pinna to kind of measure them. But what we are doing is we are literally breaking down the pinna and the individual Shaw modes and the functions of individual how should I say, regions in the pinna. You have your how should I say, you have the fossa, you have the concha, you have multiple different regions in the pinna itself that basically act as Helmholtz resonators individually and kind of resonate in tandem. So our technology using neural networks actually identifies this and does that. So if you have a picture of their ear, we can definitely do that. Are neural networks helpful in medicine? Definitely. They are useful in all aspects, especially cancer treatment, even COVID actually. So recently there was a paper which trained X-ray images of lungs to find COVID, and the accuracy of that was like 99%. So you could actually feed an X-ray image to a computer, and within 1 second it'll tell you whether the patient is COVID positive or not, which was very interesting. So that will actually take a lot of overhead from doctors, which have to physically look and look at all the different signs of whether a person is COVID positive or not. So that's something that is also being applied right now. Cancer patients, like basically brain tumors and stuff like that, there have been reports of neural networks being accurately identifying brain tumors when neurosurgeons themselves could not look at the thing and identify. But after extensive testing and more, so there are multiple in medicine, right? You have your CT scan and then you have your PET scan, and a CT scan is very routine and a PET scan is very like. So what people did was they asked neural networks to identify cancer, asked neural networks to identify tumors from a CT scan, and then verified them with a PET scan. So in the CT scan, they were not visible to the human eye, but still the neural networks found those tumors, which were actually present in the PET scan. So you found them. So the doctor were like astonished that they found them in the PET scan. So if they hadn't gone for the PET scan, that patient would have been just cleared and would have probably been dead by the time they, if they let him live for that period of time. So that's something that are used in medicine as well. Okay, Mujahid Hussain. I mean that learning process is related to the strength of coupling between neurons. The more strong the coupling, for more information is stored. Yes and no. Partially it is correct, Mujahid. So basically what happens is your neurons, right, how they operate is they don't actually work in tandem. For some neural networks they do, like a convolutional neural network where your weights are heavily correlated in terms of how they're placed, but for an artificial neural network they're not. So if you do couple between neural networks, sometimes it's called a restricted Boltzmann machine as well. You can share information between your nodes and kind of train them better. So, but you have to have the right conditions. So you have to enforce orthogonality or sparseness to kind of encode more information into each node. So to answer your question, yes or no, depending on the type of the neural network. Chandrajit Yadav, how many types of neural networks are there? As many as you want. There is no limit actually. People keep coming with new neural networks all the time. Like I also know like the few that I've read. There are so many neural networks that even I don't know about.
Yes, any questions? Dear participants, if you have any questions, you can type in chat box. Yes, Nikhil, I think there is no question from participant side.
Okay.
Okay. Nikhil,
Mm-hmm.
what are the mathematical models generally used in 3D audio and
Mm-hmm.
AI? Mathematical models.
For 3D audio and AI, so there are multiple actually. So in the late 1970s, right, when MIT started doing this, they started actually modeling the PINA function as measurement. So actually the CPIC database, right? Let me actually open. I'll present my screen and I'll show you something. Let's see. Let's see. Go back to this. So let's say CPIC chart database. So if you go here, right, they have their own paper, and where's that paper? I think it's this. Yeah. So basically, if you look at CPIC database, right, they also tried doing something similar, where in their images also they have these measurements. So per person, right, they took all of these measurements and they tried to predict the HRTF depending on this. But what happens is mathematical models can only take you a certain distance. Yes, it is true that these measurements are very important and your HRTF is a function of that. But it is not just these measurements, but also how they kind of interact with each other. So mathematical models in the late 1970s started with transmission line models, where they were looking at the ear shapes as impedances and kind of modeling them as inductors and capacitors to model resonances and notches. So basically, that's how they were designing with high Q, low Q, and that's what led to basically your physical modeling or numerical modeling approaches, which basically captured the size and shape of the human ear and kind of so transmission line led to Helmholtz resonators, which were coupled together. And then when we got more understanding of how Helmholtz resonators are coupled together, then they moved on to that. Then from Helmholtz resonators came Shaw modes. So if you talk about Shaw modes, I can show you Shaw modes.
Convolution theorem and all that. Helmholtz function.
Yeah. So basically, convolution is
convolution.
Yeah.
Fourier series,
Yeah. So
inverse Laplace and all that.
Yeah. So basically, what happens is Fourier transform is just used to kind of. So if you look at this, right, this is nothing but a Fourier transform of the recordings for the left and right ear, right? So this is nothing but Fourier transform mapped along the frequency axis. This is the FFT, fast Fourier transform, and then you can see these spectral characteristics that you can't see in the time domain. And that's what led to people going into modeling the frequency domain. So first they were trying to model the time domain because they had phase analysis. They knew that some sounds were reaching earlier than the other, and then some sounds were lower in amplitude. So you can see the phase difference and the amplitude difference in the time series, but you can't see the frequency differences in the time series. So you have to convert it into the Fourier. You have to convert it into the Laplace domain or the Fourier domain basically. So usually in terms of audio, right, you talk about Fourier domain because you are guaranteed stability in the Fourier transform, because Fourier transform is nothing but Laplace transform on z equal to 1 circle. It will map like that. So you are guaranteed stability. So you only deal with Fourier transform. So when you take the Fourier transform of these signals, right, you come across these sort of patterns which are vastly different for different human beings. So then they started modeling frequencies themselves depending on the dimensions. And then came machine learning, which actually found out, like, actually, I'm really proud to say this, but we were kind of like the pioneers of this field, where we started finding out. regions of regions that kind of interact with each other and basically come up with predictions that we had never found before. Like people just couldn't do that prior to like 2014. That's also related to like the advancement in machine learning, the advancement in computing technology, because of which we could train huge models as well, because the amount of complexity that we have in our neural networks. If you talk about the perceptron that I showed over here, right, somewhere over here, this is going to take like what, if you have 4 weights, float 32, so like 32 bits into 4, that's like what, 128 bits. So 128 bytes is like nothing to store,
Okay.
versus the models that we train are in like 15 16 GBs, and that too on GPUs. So it's like advancements in machine learning and computing technologies that has helped us to kind of come across this this domain.
Thank you so much, Nikhil. Yes, any questions from participants? Is there any chat box? Any question? Okay. Uh, on behalf of our efficiency board, respected principal, Dr. Nikhil, our HOD, Professor Namrata Javeri, Professor Dinesh Himatsingani, Vice Principal, Coordinator IPC, and Physics faculty, then Stephanie Madam, Sima Madam, Lakshman Sir, Sunam Madam, and our support staff. We are very thankful, Nikhil Sir, for your informative presentation regarding neural network, basics of neural network, different types of neural network, and then what are the applications of theoretical mathematical models for our daily life. Thank you so much, Nikhil Sir, for your information.
No problem, it is my pleasure.
Yeah.
And if any one of you has any other questions, I'll hand over my email address to Milind sir, who can then distribute it to you.
Sure.
I'll also hand over my presentation to Milind sir, so you can view it as a PDF if you want to refer it.
And I will share with our participants. And if they have any queries or any suggestion, they can directly contact.
Definitely. Most appreciated.
Yes. Thank you so much.
Okay.
Nikhil, we will close this session.
Okay. Thank you. See you all. Good night from here.
Sir.
Yeah,
Thank you.
all participants. Thank you very much.
We'll get this our feedback link.
I will share on feedback assessment form and feedback on 28th of June.
Sir, should I make you the host, Milind sir, and leave?
Okay. Me to... Yes.
Okay. Thank you all.
Thank you, Nikhil. Thank you.
See you guys.
As the feedback link कहाँ पर आएगा?
Feedback will on 20th of this month we will share feedback link and assessment.
On our mail?
Yes. I will email you. No problem.
Okay.
Thank you.
Thank you.
Thank you. Dear all, thank you so much for your participation.
Honorable Speaker Nikhil Javeri, University of Southern California, LA, US, President Excellencies, teachers and my dear friends. I thanks college for giving me the opportunity to express my gratitude on this special day. On behalf of the trustees, management, Hyderabad Sindh National Collegiate Board, HSNC Board, our respected principal, Dr. Neha Jaktine ma'am, Head Department of Physics, Professor Namrata Javeri ma'am, Professor Dinesh Himatsingani sir, Vice Principal and Coordinator IQAC, Dr. Lakshman Jatar sir, Professor Steffi Sara ma'am, Dr. Sima Shinde ma'am, and Professor Punam Jaju ma'am. I express my heartfelt thanks to my guest speaker, Mr. Nikhil Javeri, Research Engineer MS from University of California. Your speech, sir, was inspiring and will guide us in sense of importance as well as significance of fundamental study of basic sciences or fundamental principles of basic sciences such as physics, chemistry, mathematical sciences, stats, biological sciences, etc. In your speech on real life applications of a neural network, 3D audio, I will just summarize your speech, and there are main points from your speech or outcomes of your speech. You explain about the heavily reliant of linear algebra, that is inclusion of matrix operations, probability theory, vector analysis, statistical methods. You explain also explain about the most common neural networks like artificial neural network, AN, deep neural network DNN, convolutional neural network, that is CNN, and recurrent neural network RNN, generally used for generic applications, then different layers in depth, and to take raw data directly, then image processing, video processing, then time series data like conversion of speech to text or text to speech. You also explain about the neural networks applications in terms of classification and regression, then concept of sound and audio, that is sound is the energy based event, where audio is the electrical representation of sound. Then you also explain about the four fundamental different things that happen when human listens to the same sound sources in real life. Then concept of interaural time difference, that is ITD, concept of interaural level difference, that is ILD. Then what is the meaning of body occlusion, pinna related transfer function, that is PRTF. Then what are the prerequisites for designing of customized headphones, and these are the summary of your lectures. Again, big thank you for your informative session. I would like to thank all the respected representatives who have blessed us with their presence. I would also like to thank our technical team, Professor Manish Karale, Professor Akshay Nimkar, Professor Akbar Khan, Professor Kaizat, and Professor Manoj Kadam. Thank you very much once again. Finally, once again, I thank you, big thank you, Mr. Nikhil Javeri, respected representatives and officials of participating colleges and universities. Thanks again for making this conference a success. Thank you so much. Now I am ending this session. Thank you so much.